Have you ever had trouble in calculus to the point of reconsidering your life choices up to this point? Don't worry anymore, my friend, because I'm going to show you how to do 5 topics in calculus.
X gon' give it to you. Wait for you to get it.
So you know when you integrate this equation, you get the antiderivative of it plus the little c at the end. Pretty simple thing to do. What if calculus wanted to toss in a whole new way of making life a little bit more difficult by adding either trig, exponentials, and adding some random x's here and there? Well, I give you this. In hindsight, it's not a very difficult equation to integrate, but it's the first one I thought up and we'll just roll with it. To integrate by substitution, you would have to use another variable, like u. To choose u, you want to try and find as many parts of the equation to cancel. I started with tangent x squared as my u. Now you want to try to take the derivative of u to get du. Now we have du equals 2x secant squared of x squared. See that we have a similar part of the equation as our du. Now we'll just plug and play. We are left with du, and now we'll integrate for du. We follow up the power up rule by adding the exponent by adding 1 to the exponent and dividing by what the exponent equals. Afterwards, we'll replace u for tangent of x squared. And we get this. Now I have another one. The integral of sine of 1/2 x times cosine of 1/2 x all over 2. Now again, let's pick a part to use as u. Let's pick sine of 1/2 x, hint hint wink wink. Now we take the derivative to get du, and get a similar part of the equation. Now we do replace everything with u and du, and integrate for u, and end up with sine of 1/2 x over 2 plus c.
On your own, X gon' deliver to you. Knock, knock, open up the door.
Now we are in a topic that I hated with extreme passion of 6 fiery dragons dancing the tango on top of the sun. Now, what if you have the integral that you couldn't just do by substitution? Ba-ba-ba-bang! Here you go. And now let's do it step by step to integrate this equation by parts. So, we'll start off using this lovely equation, uv minus the integral of du. You must be asking yourself, but Nathan, how do we know what v and u? As you start heating up out of anticipation, well, people, you should have just waited another second because this is how, with this acronym, LIATE, logs, inverse, arithmetic, trigonometry, and exponential. Whatever comes first is your u, and second becomes v. 3x would be our u, and cosine dx would be our dv, since of the dx. Now we'll fill in the box. Now we'll plug and play. We'll end up with 3x sine of x minus this integral of 3 sine of x dx. Now we have to integrate the integral and get 3 cosine plus c. And we'll end up with 3x sine of x minus 3 cosine of x plus c. Now we have a new equation of x squared times the ln of x. ln would be our u, and x squared dx will be our dv. Now we'll fill in the blocks. And now we'll plug and play in the equation, and get x cubed over 3 times ln of x minus the integral of x cubed over 3x. We're going to clean it up by pulling out the 1/3, and we are left with x squared. We'll integrate it and multiply it by 1/3 and get x cubed over 9. And now we'll end up with x cubed over 3 times the ln of x minus x cubed over 9 plus c. Now we are in a topic that was near the early middle-ish part of the year that I had trouble with, even though it was probably the easier parts of calculus. Look at this one, nothing real ugly about it, so we'll just get its derivative. So to start, we'll be using the power down rule. Bring the exponent to the front and subtracting 1 from the power. Now we take the derivative of the inside function, and add back the inside function you took the derivative of. Now a different equation, the square root of 6x plus 6. Since the square root really means the function to the power of 1/2, we can use the power down rule. Then we'll take the derivative of the inside function and end with 3 times the quantity 6x plus 6 to the power of negative 1/2.
I got such a good heart that I make the mother wonder if you did it. Damn right.
This one topic made me think harder than a philosopher contemplating the answer to the universe. Because 1, you have to remember the past formulas of area, perimeter, and volumes for every shape possible. There's a lot of abstract thinking that I never do. And we end up differentiating equations, which I wasn't good at yet. So, we'll say that a guy asks you for a certain box that can hold about 69 centimeters of space inside with a reasonable dimensions. So, start contemplating how to build this said box. So you start thinking, I know this volume is base times height times length, and he wants 69 centimeters of space. Remembering that he wanted a box, we can conclude that we only need an x and a y, or just an x. And this would be our volume equation. Since we needed the dimensions of the box, we'll be messing with the perimeter of the box, which will be 8x plus 4y. So we plug in our 69 centimeters into the volume equation. Since it will be easier to mess with one variable at a time, we'll move the x over to the other side. Now we'll plug in our new equation into the perimeter equation. Now we take the derivative of the equation and solve for 0. We end up with 4.101 as our x. And now we'll plug it back into the volume equation to find y. And we get our dimensions. Now we have a dude that wants a perimeter of 120 meters of area, with the most area he can get. We know the equation for the perimeter, so we can set up the equation as 120 plus equals 2x plus 2y. Then we can simplify it. We know the area is base times height, so we solve for y. And plug it back into the area equation, and we get the derivative. Now we solve for 0, and we get 30, and now we plug it back into the original equation and solve for y. We get 30 for both x and y.
And I do it again, 'cause I am light, so I got to win.
Finding the volume of the solid of revolution is a tricky subject that gave me trouble for about maybe 5 days. Because 1, to find the volume, you have to integrate the area the solid of revolution created, the area dependent on the shape produced, the boundaries used dependent on the axis used, and the variable used dependent on the axis the solid of revolved around. So we have this mess, the graph of square root of x and x equals 4. It tells us that it revolves around the x-axis. The shape it makes is a circle when it's spinning. So to figure this out, we know that this is the equation for volume. This is our boundaries. We know the circle of the area is pi times r squared. So our equation that is graphed is r in the equation. So we plug it in and we can simplify the equation. And now we integrate it. And now we plug in the boundaries and subtract. We plug and subtract the boundaries. Times it by pi and get 8 pi. Now here's a solid that requires a little different method to solve its volume. We know that there's a space in the solid with different radii. Anyways, we'll use the washer method, which is the outside radius squared minus the inside radius squared, which acts as our variable. We'll label these as big brother r and little bro tiny r. We have 3 as our outside radius, and since it revolves around the y-axis, we have to do the square root of y as little r. So, to solve this, we use the almost exact same way as the last example. But for our x/y, we have to do the big R squared minus the little r squared. We'll plug in our r's and simplify it. Now we plug in the volume equation, simplify it, and integrate it and solve for the boundaries. Simplify, keep simplifying, even more simplifying, then times by pi, and this is your answer. Hey guys, thanks for watching this video. And if you enjoyed it, no joke at all, no scam at all, if you give this video a like, I will give you, one monkey butler. Yes, place under your pillow after you like this video. But seriously, thank you for watching, and I'm out. Peace!